If you close your eyes and picture the universe in its most fundamental form, you might imagine an expanse of stars, galaxies, and infinite darkness stretching beyond comprehension. It's a place so vast, so unexplored, that even the most brilliant minds have yet to unlock all of its secrets. The idea that the universe holds more than we can perceive isn't new. Throughout history, humanity has gazed at the night sky, contemplating the unknown, driven by a thirst for knowledge about where it all began. In the vastness of space, there are mysteries that transcend our understanding of time and existence itself. What we know about the origin of the universe, for example, comes from the Big Bang theory, a concept that has shaped much of modern cosmology. Around 13.8 billion years ago, everything we know, every particle, every galaxy, was once compressed into a single point. This singularity, unimaginably dense and hot, exploded in an event that still continues to echo across space. From this explosion, space itself began to stretch, and the universe expanded outward, creating everything we observe today. The Big Bang is considered one of the most important and well-supported theories in science, underpinned by observational data, such as the cosmic microwave background (CMB), the afterglow of the Big Bang, which provides a snapshot of the universe when it was just 380,000 years old. But this idea, while grounded in science, is not as simple as it seems. The very nature of the Big Bang, this origin of everything, remains elusive. How did such an event occur? What was there before the Big Bang? These questions continue to plague even the most learned scientists, because every theory we have about the universe's beginning only raises more questions. Theories like quantum fluctuations and multiverse hypotheses attempt to explain what happened before the Big Bang, but they remain speculative. For years, scientists have been trying to piece together the puzzle of the universe's origin, but with each discovery, we realize just how much more there is to understand. One of the biggest mysteries, one that has captured the imagination of humanity for decades, is the Fermi paradox. Imagine this, with billions of stars and even more planets scattered across the galaxy. The possibility of extraterrestrial life seems overwhelmingly likely. If life could arise on Earth, why wouldn't it exist elsewhere in the vast universe? Yet, despite the countless planets out there, we have not received a single signal from another intelligent civilization. This paradox forces us to ask, where is everyone? Why, in such a vast and populated universe, do we appear to be completely alone? This question becomes even more perplexing when we consider another enigma, Ober's paradox. It's one of those questions that seems simple on the surface, but leaves you pondering. The night sky is filled with stars, millions, billions, even trillions. But when we look up, we see only darkness. The universe is supposed to be full of light, so why isn't the night sky brighter? This paradox challenges the way we think about space and our place in it, hinting that the universe may be much more complex than we can ever imagine. What's even more baffling are the unexplained phenomena we encounter in space. Strange stars have vanished without a trace, and planets like the mysterious missing planet Dagon have disappeared into the abyss of the cosmos. These disappearances defy logic, suggesting that the universe is not just a place of matter and energy, but one filled with hidden forces and uncharted realms. What could be the cause of these strange occurrences? What do they tell us about the fundamental nature of space? Despite all these questions, there's one thing that scientists do know for certain: the universe is expanding. The remnants of the Big Bang still linger in the form of cosmic background radiation, a faint echo that travels across the universe, providing us with a glimpse into its early stages. This radiation is a key piece of evidence in understanding the Big Bang and the continuing expansion of the universe. In fact, scientists have observed that galaxies are moving away from us at an increasing rate, a discovery that led to the formulation of the theory of dark energy, an enigmatic force that makes up about 68% of the universe, pushing galaxies apart at an accelerating rate. But even as we observe these remnants, we are only beginning to scratch the surface of what the universe truly is. This is where the mystery lies. What we think we know is just a small fraction of the whole story. The universe continues to expand, yet we still don't fully understand its origins. The more we discover, the more questions arise. leaving us to wonder whether we will ever truly understand the universe's deepest secrets. And if that wasn't enough, there's still another mystery: dark matter. Dark matter, a substance that cannot be seen but exerts an invisible force on the visible matter around it, makes up about 27% of the universe's mass. Yet, despite its overwhelming presence, we have never been able to detect it directly. It's one of the greatest scientific challenges of our time. What exactly is dark matter, and how does it affect the universe? The answer remains one of the most profound and elusive puzzles of modern science. Observations from galaxies, galaxy clusters, and gravitational lensing have provided indirect evidence of dark matter's existence, yet its true nature remains a mystery. Then there's dark energy, an even more enigmatic force that seems to be accelerating the expansion of the universe. While dark matter holds galaxies together, dark energy seems to be pulling them apart. It makes up around 68% of the universe, yet its true nature is still completely unknown. Could this force be responsible for the ever-increasing rate of expansion? If so, how can we begin to understand its impact on the future of the universe? These are questions that continue to perplex physicists and cosmologists alike. As if these mysteries weren't enough, there are also peculiar phenomena that defy current understanding. Spacecraft like Galileo and Rosetta have experienced unanticipated changes in their velocity during flybys of planets. These anomalies suggest that there may be unknown forces acting on these spacecraft, forces that we have yet to identify. Could these strange occurrences point to new, undiscovered aspects of physics? Are there forces at play in the cosmos that are still beyond our understanding? What makes these discoveries so intriguing is that each one forces us to reconsider our understanding of the universe. With each unanswered question, the universe becomes even more mysterious. And it's this very mystery that drives us to explore, to search for answers, and to unravel the secrets hidden within the stars. As we continue to investigate, we learn more not just about the universe, but about ourselves. The universe reflects the fundamental questions of human existence. Where do we come from? Why are we here? What is our purpose? These are questions that have driven philosophers, scientists, and explorers for centuries. And though we have made incredible strides in understanding the cosmos, the answers to these questions still elude us. The journey of exploration is ongoing, and with each discovery we uncover new layers of the universe's complexities. But the greatest mystery is that for all we know, the universe is still full of surprises. There may be forces, dimensions, or realms of existence waiting to be discovered, hidden beneath the surface of what we currently understand. Perhaps that's the true beauty of the universe. It's a place of infinite wonder and possibility. The more we learn, the more we realize how little we truly know. And in this mystery there lies a sense of awe, a sense of wonder, and a deep yearning to keep exploring, to keep searching, and to keep asking the questions that bring us closer to understanding the vast and enigmatic cosmos we call home. The universe, as vast and complex as it is, presents us with a series of puzzles that seem to have no easy answers. These paradoxes aren't just mere curiosities, they are fundamental mysteries that challenge our very understanding of the cosmos, forcing us to rethink not just what we know but how we know it. Each question we encounter in our exploration of space presents a new frontier of inquiry, where data points and scientific observations illuminate one part of the puzzle, only to reveal deeper complexities beneath the surface. One of the most fascinating and enduring paradoxes is the Fermi paradox, which asks a simple yet profound question. Why haven't we found any signs of extraterrestrial life, despite the vastness of the universe? The question is rooted in the seemingly simple idea that with billions of stars in our Milky Way galaxy alone, each potentially hosting planets in the habitable zone, intelligent life should be common. If we consider that there are over 100 billion stars in our galaxy, an estimate suggests that as many as 20% of these stars could have planets in their habitable zone, it seems almost inevitable that life exists somewhere else. The observable universe is even more vast. With over 100 billion galaxies, each containing billions of stars, there are trillions of planets scattered across space. According to the Drake equation, which attempts to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way, the number of civilizations could be anywhere from a few hundred to as many as millions. Yet, despite all the potential for life in the universe, we have found no definitive evidence of extraterrestrial civilizations, no signals, no clear signs, no definitive contact. To understand the enormity of the issue, consider the distance between us and the closest potentially habitable planet, Proxima Centauri b, located about 4.24 light-years away. Even if we could send a spacecraft to Proxima Centauri at the fastest speeds we currently have, about 38,000 miles per hour, it would take over 70,000 years to reach it. The vast distances between stars make interstellar communication or travel incredibly challenging, which might explain why we haven't heard from other civilizations. The paradox goes beyond mere distance. One of the possible explanations is the concept of the Great Filter. This theory suggests that while intelligent life may be common, it is incredibly rare for civilizations to reach a stage where they can communicate or travel across the stars. The Great Filter may be a barrier that prevents civilizations from advancing past a certain point, perhaps due to self-destruction through war, environmental collapse, or other existential threats. Some even argue that we may be living in the middle of this Great Filter, and the true danger might lie ahead for us. Another hypothesis proposes that extraterrestrial civilizations may be deliberately avoiding us. Known as the zoo hypothesis, this idea suggests that advanced alien species may be aware of humanity but choose not to contact us, similar to how we observe animals in a zoo without interfering with their natural behaviors. Perhaps these civilizations see us as too primitive or unready for contact, and their non-interference is an ethical choice. If true, it would mean that the lack of communication isn't a result of distance or extinction, but of deliberate choice. Yet, even with all these possibilities, the absence of evidence continues to puzzle scientists. In 1974, astronomers sent a radio signal, the Arecibo message, into space in an attempt to make contact with extraterrestrial life. This 679-bit message, encoded into binary, was aimed at the star cluster Messier 13, which is about 25,000 light-years away. If any intelligent civilizations exist in that cluster, they would receive the message in about 25,000 years. This symbolic gesture represented our hope to communicate with the broader universe, but it also highlighted the difficulty of sending signals across such immense distances. And with no response yet, the question remains, where are they? This lack of communication leads us to ponder the vastness of space itself and the paradoxes that space poses on a larger scale. Olbers' paradox, named after the German astronomer Heinrich Wilhelm Olbers, asks why the night sky is dark when the universe is filled with an infinite number of stars. The paradox stems from a seemingly simple observation: if the universe is infinite and contains an infinite number of stars, then every line of sight should eventually hit a star, meaning the sky should be completely bright, not dark. The resolution to this paradox lies in the understanding that the universe is not static, it is expanding. The universe has been expanding since the Big Bang, which occurred around 13.8 billion years ago. This expansion stretches the wavelengths of light emitted by distant stars, shifting them into the infrared or even radio wavelengths, making them invisible to the human eye. Additionally, the observable universe is not infinite, and because of the finite speed of light, the stars we see are not the stars that exist today, but those that existed billions of years ago. The universe's finite age means that there simply hasn't been enough time for light from all stars to reach us, especially from the most distant galaxies. Moreover, the universe continues to expand, and as it does, light from distant galaxies is redshifted, stretched into longer wavelengths, making it even less likely that we will ever see light from these far-off stars. What seemed like a paradox is now understood as a consequence of the dynamic nature of the cosmos, as space itself stretches and changes over time. Yet the universe continues to reveal its mysteries. One of the most profound questions about the cosmos is the existence of dark matter. While we cannot see dark matter directly, we can observe its effects on the motion of galaxies and clusters of galaxies. Through the study of galaxy rotations, scientists discovered that galaxies rotate at such speeds that, if they were made of just the visible matter we can observe, they would fly apart. The gravitational pull exerted by dark matter is what keeps galaxies intact, providing the necessary gravitational force to prevent them from disintegrating. Dark matter was first hypothesized in the early 20th century by Fritz Zwicky, who noticed that galaxy clusters were moving faster than they should be based on the amount of visible matter present. Later, Vera Rubin and W. Kent Ford conducted detailed observations of spiral galaxies and discovered that the outer stars of these galaxies were moving much faster than expected. Their findings pointed to the existence of a mysterious, invisible substance, dark matter, that made up most of the mass of the galaxy. In fact, dark matter is thought to constitute around 27% of the total mass and energy content of the universe, while visible matter makes up only about 5%. The remaining 68% of the universe is made up of dark energy, a force that seems to be driving the accelerated expansion of the universe. Discovered in the late 1990s through observations of distant supernovae, dark energy acts in opposition to gravity, causing the universe to expand at an ever-increasing rate. Unlike dark matter, which exerts a gravitational pull, dark energy seems to have a repulsive force, pushing galaxies farther apart from one another. The exact nature of dark energy remains one of the greatest mysteries in modern cosmology. Some theories suggest that dark energy is linked to the energy of the vacuum of space, while others propose that it is a fundamental force in nature that we have yet to understand. These discoveries, the existence of dark matter and dark energy, have reshaped our understanding of the universe, revealing that the majority of its content is invisible and mysterious. While we can observe the effects of dark matter on the motion of galaxies and measure the expansion of the universe to understand dark energy, we still have no direct evidence of either of these phenomena. The very fact that they exist and are so central to the universe's behavior suggests that there is much more to the cosmos than we currently perceive. As if these phenomena weren't enough to contend with, cosmic anomalies continue to intrigue and challenge scientists. Spacecraft such as Pioneer 10, Pioneer 11, and others have experienced unexplained deceleration as they travel away from Earth. This phenomenon, known as the Pioneer anomaly, has left scientists scratching their heads for decades. Though many initially believed it could be the result of a small, unaccounted-for force, perhaps the release of gas from the spacecraft's power system, this explanation didn't fully account for the behavior observed. The anomaly suggests that there may be forces at play in space that we don't yet understand, forces that could reveal new aspects of physics, especially at very large scales. Similarly, the flyby anomaly, in which spacecraft such as Galileo and Rosetta experienced unexpected changes in velocity during planetary flybys, raises questions about our understanding of gravity and space-time. These anomalies have led some scientists to speculate that there may be unknown forces affecting spacecraft trajectories, which could revolutionize our understanding of how objects move through space. Each of these anomalies and paradoxes challenges our current understanding of physics and the cosmos. They are not just academic puzzles, they force us to confront the unknown and to acknowledge the limitations of our knowledge. The universe is full of surprises, and every new mystery uncovered reveals more about the complexity of the cosmos. The vastness of the universe is both humbling and inspiring. The more we learn about the cosmos, the more we realize how much there is left to discover. Each paradox, each anomaly, each unexplained phenomenon invites us to keep asking questions, to keep exploring, and to keep reaching for the answers that are just beyond our grasp. The universe in all its mystery continues to challenge us, but it is also the ultimate canvas for human curiosity, a canvas we have only just begun to explore. As we look deeper into the universe, we realize that the search for extraterrestrial life is only one piece of the puzzle. The vastness of the cosmos not only raises questions about the potential for life, but also about how the universe works on a fundamental level. How do celestial bodies form and evolve? What laws govern the movements of planets, stars, and galaxies? And more fundamentally, are we truly alone in the universe? While the question of life beyond Earth may be one of the most compelling, there is much more to explore, phenomena that are no less fascinating, if not more so. One of the most profound and fundamental questions humans have asked is, are we alone? The pursuit of an answer takes us beyond the realms of our own planet and into the depths of the universe. The sheer size of the observable universe suggests that life might be widespread, but proving it is an entirely different matter. The search for extraterrestrial life has been one of humanity's most ambitious projects, and yet, despite our advances, we have found no definitive evidence of life beyond Earth. The first step in answering this question lies in understanding the habitable zone of a star. A habitable zone is a region around a star where conditions may be just right for liquid water to exist on the surface of a planet, a crucial ingredient for life as we know it. When astronomers began finding exoplanets, planets that orbit stars other than our Sun, they found that many of these planets existed in what is called the Goldilocks zone. This is the region around a star where it's neither too hot nor too cold for water to remain liquid. In 1995, astronomers discovered the first exoplanet in this habitable zone, 51 Pegasi, the C, orbiting a Sun-like star located 50 light-years away. Since then, the discovery of thousands of exoplanets has expanded our knowledge of the cosmos. As of now, astronomers have identified over 5,000 confirmed exoplanets, many of which lie in their stars' habitable zones. These planets offer exciting possibilities. Could one of them harbor life? Could life exist on a planet completely different from Earth, perhaps in a place where the conditions for life are entirely foreign to us? The discovery of planets in the habitable zone of distant stars suggests that life elsewhere might not be as rare as once thought. Still, even with thousands of exoplanets discovered, the question remains, how do we find the one planet where life exists? One of the most intriguing methods of finding extraterrestrial life is through the search for biosignatures, indicators that life, either past or present, exists on a planet. This could include gases like oxygen, methane, or carbon dioxide, which are produced by living organisms. For instance, the discovery of methane in the atmosphere of Mars has sparked debates about whether it could be a sign of microbial life. Similarly, scientists have looked for signs of life on Europa, one of Jupiter's moons, which is covered by an ice shell and may harbor a subsurface ocean. Here, the potential for microbial life is high, as deep ocean vents on Earth, where life thrives without sunlight, provide a compelling model for how life could exist in the dark, icy depths of Europa. Another avenue for the search for life is through the SRT, Search for Extraterrestrial Intelligence program, which has been scanning the skies for decades, looking for radio signals or other transmissions from alien civilizations. The concept of SETI was born in 1959 when scientists proposed that we might be able to detect alien life through the detection of artificial radio signals. The program has evolved significantly since its inception, with modern techniques now using sophisticated algorithms and vast computing power to analyze signals from space. Despite this, SETI has yet to find a definitive signal, and the Fermi paradox continues to challenge our assumptions about extraterrestrial intelligence. But perhaps as technology advances, the signals we seek will eventually be found, whether they're radio waves, light pulses, or something entirely unexpected. In the ongoing search for life, we're also confronted with the question of what life might look like. Given that Earth life is carbon-based, many scientists assume that extraterrestrial life will share similar biochemical foundations. However, there are also ideas that challenge this assumption, suggesting that life could be silicon-based or even based on some other molecular structure entirely. In fact, astrobiologists have proposed the possibility of life forms that don't rely on water at all, such as life that could exist in environments far colder or hotter than anything earthbound organisms can tolerate. For example, some of the most extreme life on Earth, extremophiles, thrive in conditions previously thought to be uninhabitable. Microbes have been found living in the boiling hot springs of Yellowstone, in acidic lakes, and even deep under the Earth's surface. These findings suggest that life might be far more adaptable than we realize, and extraterrestrial life could exist in environments radically different from those on Earth. But what about intelligent life? If life is common in the universe, does it necessarily follow that intelligent life is as well? Many scientists argue that the evolution of intelligence is rare. After all, on Earth it took billions of years for humans to evolve from simple single-celled organisms into the complex societies we have today. What were the chances of this happening elsewhere in the cosmos? And if it did, would an intelligent civilization be able to survive the challenges it faces, like war, climate change, or resource depletion? The potential for intelligent life also brings us to one of the most fascinating possibilities, the idea of interstellar communication. If we were to find an intelligent civilization, how could we communicate with them? The distance between stars is so vast that even light traveling at 186,000 miles per second would take years, if not millennia, to travel from one star system to another. This means that communication across interstellar distances is not only difficult but may be completely impractical. However, mathematics could provide a universal language. Some scientists believe that the best way to communicate with extraterrestrials would not be through spoken language but through mathematical principles. Numbers, shapes, and equations are concepts that are likely to be understood by any intelligent species, regardless of their biology or culture. For instance, prime numbers or geometric shapes like the Fibonacci sequence might serve as the perfect introduction to a message from one civilization to another. And then there are the ideas that sound more like science fiction but are based on real scientific theories. For example, the Kardashev scale, a concept first proposed by Russian astrophysicist Nikolai Kardashev in 1964, classifies civilizations based on their energy consumption. A Type 1 civilization can harness the energy resources of an entire planet. A Type 2 civilization can harness the energy of a star, for example, using a Dyson sphere, and a Type 3 civilization can control energy on the scale of an entire galaxy. Humanity is not yet a Type 1 civilization, but we are making progress. Our energy consumption and technology are growing exponentially. Could we one day become a Type 2 or even a Type 3 civilization? This idea invites speculation on the future of humanity and our place in the cosmos. In addition to the search for life, there are other cosmic phenomena that continue to challenge our understanding of the universe. For instance, black holes, regions of space where gravity is so strong that not even light can escape, have fascinated scientists for decades. We now know that black holes are not just theoretical, they are real and detectable. They can be observed indirectly through their gravitational effects on nearby stars and gas clouds. In April 2019, the Event Horizon Telescope (EHT), a global network of radio telescopes, captured the first ever image of a black hole located in the galaxy M87. The image, which showed a dark shadow surrounded by a glowing ring of hot gas, provided direct evidence of a supermassive black hole, something that had been theorized for decades. Similarly, gravitational waves, ripples in space-time caused by massive objects accelerating, were first detected in 2015 by the LIGO Laser Interferometer Gravitational Wave Observatory collaboration. These waves were produced by the collision of two black holes 1.3 billion light-years away. Gravitational waves open up a new way of studying the universe, allowing us to observe cosmic events that were previously invisible. The detection of these waves was a major breakthrough in our understanding of the fabric of space-time itself. There is also the fascinating field of exoplanet studies, the search for planets outside our solar system. As of today, astronomers have confirmed over 5,000 exoplanets, and thousands more candidates are waiting to be confirmed. These planets vary greatly in size, composition, and orbital characteristics, but many of them lie in the so-called habitable zone of their stars, where conditions may be right for liquid water to exist. The discovery of these exoplanets has revolutionized our understanding of planetary systems and has opened up new possibilities for finding life beyond Earth. In our quest to understand the universe, we have made remarkable strides, but the journey is far from over. Each new discovery brings new questions, and each answer opens up even greater mysteries. We are still just beginning to scratch the surface of what the universe holds. Whether it's the search for extraterrestrial life, the study of black holes, or the exploration of distant planets, the future promises to be filled with new revelations that will continue to expand our understanding of the cosmos and our place in it. As we continue to explore the wonders of the cosmos, we quickly realize that space is more than just the vast emptiness between stars. It's a dynamic, constantly evolving system, shaped by the forces of nature that govern it. Some of the most fascinating and complex phenomena in the universe arise from the very forces that give birth to galaxies, stars, and planets. The gravitational interactions between these celestial bodies form the basis for many of the patterns and structures we observe in the universe. One of the most striking and awe-inspiring phenomena is the formation and behavior of black holes. These enigmatic objects, once thought to be mere theoretical curiosities, have now become an integral part of our understanding of space. Black holes are regions of space where gravity is so strong that not even light can escape. They are formed when massive stars collapse under their own gravity at the end of their life cycle, compressing all their mass into an infinitely dense point known as a singularity. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. While black holes may seem like cosmic vacuum cleaners, devouring everything in their path, they are actually incredibly important for the structure of the universe. For one, black holes play a crucial role in the formation and evolution of galaxies. Supermassive black holes, which can have masses equivalent to billions of times that of our Sun, are thought to reside at the center of most large galaxies, including our own Milky Way. These supermassive black holes may help shape the galaxies they inhabit, influencing star formation and the distribution of matter. The center of our galaxy, known as the galactic center, houses a supermassive black hole called Sagittarius with a mass of approximately 4 million times that of the Sun. Recent technological advancements have allowed us to observe these distant cosmic objects in unprecedented detail. In April 2019, the Event Horizon Telescope EHT collaboration released the first ever image of a black hole located in the galaxy M87, 55 million light-years from Earth. The image showed a dark central region surrounded by a bright, glowing ring of hot gas, what we know as the shadow of the black hole. This groundbreaking discovery confirmed many of the predictions made by Albert Einstein's general theory of relativity, which described the bending of space-time around a black hole. As scientists continue to study black holes, they are also delving into the mysterious properties of gravitational waves. These ripples in space-time are caused by massive objects, such as black holes and neutron stars moving or colliding. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made its first detection of gravitational waves, which were generated by the collision of two black holes. This discovery opened up an entirely new way of observing the universe, one that doesn't rely on light or electromagnetic radiation, but on the distortions in space-time itself. Gravitational waves are incredibly difficult to detect because they cause tiny distortions in space-time on the order of a fraction of the width of a proton. Yet, these waves can provide a wealth of information about the most violent and energetic events in the universe. The collision of two black holes, for example, generates gravitational waves that can be used to study the properties of these objects, including their mass, spin, and even the nature of the space-time fabric itself. As detection methods improve, scientists hope to detect more gravitational wave events, shedding light on the inner workings of black holes and other exotic objects in the universe. Another remarkable aspect of the universe is its ability to continually evolve. Stars, for example, have life cycles just like any living organism. Stars are born, live out their lives, and eventually die in dramatic and sometimes explosive ways. The life cycle of a star is primarily determined by its mass. Smaller stars, like our Sun, have lifetimes of billions of years, gradually evolving through a series of phases, from a main sequence star to a red giant, and eventually shedding their outer layers to form a planetary nebula. The core left behind becomes a white dwarf, which will slowly cool over billions of years. On the other hand, massive stars, many times larger than the Sun, follow a different and much more violent path. These stars burn through their fuel much faster, and when their fuel runs out, they collapse under the force of their own gravity, leading to a spectacular explosion known as a supernova. During a supernova, the star releases an immense amount of energy, briefly outshining an entire galaxy. The remnants of the explosion, the core of the star, can become either a neutron star or, if the star was massive enough, a black hole. Neutron stars, like black holes, are among the most exotic and dense objects in the universe. These stars are composed almost entirely of neutrons, with a mass comparable to that of the Sun, but with a radius of only about 10-20 kilometers. The surface gravity of a neutron star is so intense that it can crush matter to unimaginable densities. Supernovae are not only responsible for creating neutron stars and black holes, but also for producing the heavy elements that make up much of the matter in the universe. Elements like gold, uranium, and iron are forged in the intense heat and pressure of supernovae and are then scattered throughout space, enriching the gas clouds from which new stars and planets will eventually form. In this way, supernovae play a crucial role in the cosmic recycling of matter, ensuring that the building blocks for future generations of stars and planets are continually replenished. As we continue to explore stellar evolution, we also find that the very structure of galaxies is shaped by the life and death of stars. Our Milky Way galaxy, for example, has a spiral structure, with stars arranged in rotating arms around the central supermassive black hole. The stars in the outer regions of the galaxy move more slowly than those near the center, and over billions of years this results in a spiral shape. Galaxies like ours are constantly evolving, as stars are born, live, and die, while new stars are formed from the remnants of dead ones. However, galaxies are not static. They interact with each other in complex ways. Galaxy mergers are one of the most dramatic events in the universe. When two galaxies collide, their stars and gas clouds pass through each other without colliding, but the gravitational forces cause the galaxies to merge and reorganize. The result can be a new, larger galaxy with a completely different structure. The Andromeda galaxy, for example, is on a collision course with the Milky Way, and in about 4.5 billion years, the two galaxies will merge into a single, larger elliptical galaxy. This process is part of the cosmic evolution that shapes the universe on grand scales. The interaction of galaxies is not limited to mergers. Galaxy clusters, groups of galaxies bound together by gravity, are some of the largest structures in the universe. These clusters contain hundreds or even thousands of galaxies and are held together by the collective gravitational pull of their member galaxies. The Virgo cluster, located about 54 million light-years from Earth, is the closest major cluster to our own Milky Way and contains over 1,000 galaxies. These clusters are not just collections of galaxies, they also contain vast amounts of hot diffuse gas that can be studied using X-ray telescopes. The gas in these clusters is so hot that it emits X-rays, allowing astronomers to study the behavior of matter in some of the most extreme environments in the universe. Yet even as galaxies evolve and interact, there is one force that continues to drive the expansion of the universe itself: dark energy. Discovered in the late 1990s, dark energy is thought to make up about 68% of the universe's total energy content. It is responsible for the accelerated expansion of the universe, which was first observed through the study of distant supernovae. These supernovae, which act as standard candles for measuring distances in the universe, revealed that the expansion of the universe was not slowing down, as had been previously assumed, but was instead speeding up. This discovery was one of the most surprising findings in modern cosmology and led to the hypothesis that an unknown force, dark energy, was driving the accelerated expansion. Dark energy is still poorly understood, but it is thought to be a property of space itself. As space expands, dark energy appears to become more prevalent, pushing galaxies farther apart. The exact nature of dark energy is one of the greatest mysteries in cosmology. Some theories suggest that it could be a form of energy associated with the vacuum of space, while others propose that it could be a fundamental force that has yet to be understood. Regardless of its true nature, dark energy plays a key role in the future of the universe, determining whether it will continue to expand forever or eventually collapse back in on itself. As we look at the universe and contemplate the forces that shape it, we realize that we are only beginning to understand its true complexity. Stars are born and die, galaxies evolve and merge, and vast forces like gravity, dark matter, and dark energy shape the cosmos in ways we are only beginning to comprehend. These processes unfold on timescales far beyond our own, yet they are the driving forces behind the cosmic dance that has been happening for billions of years. We are only beginning to scratch the surface of the mysteries of the universe, and with each discovery we find ourselves faced with even more questions. But this is the beauty of the cosmos. Each answer opens the door to new mysteries, and it is the pursuit of these mysteries that keeps us looking to the stars. The more we explore the universe, the more we come to understand how incredibly vast and complex it truly is. At the heart of this complexity lies one of the most profound mysteries, the structure of the universe itself. From the smallest particles that make up the fabric of matter to the largest galaxies stretching across billions of light years, everything in the cosmos is interconnected by forces we are still trying to fully comprehend. The more we study, the clearer it becomes that the universe is not a static, unchanging place. It is a dynamic system, constantly evolving and subject to the forces of nature that govern it. One of the most fundamental forces in the universe is gravity, the force that binds everything together. Gravity is what holds planets in orbit around stars, keeps stars together in galaxies, and governs the movement of entire galaxies. Yet, despite its importance, gravity is still a source of mystery. Isaac Newton's law of universal gravitation, developed in the 17th century, was the first comprehensive description of gravity's effects. It showed that every object in the universe exerts a gravitational pull on every other object, and the strength of this pull is proportional to the mass of the objects and the distance between them. While Newton's laws worked well for many situations, it wasn't until Albert Einstein developed his theory of general relativity in 1915 that we gained a deeper understanding of gravity. Einstein's theory proposed that gravity is not a force acting at a distance, as Newton had suggested, but rather the result of the warping of space-time caused by massive objects. In other words, massive objects like the Sun cause the fabric of space-time to bend, and this curvature is what we experience as gravity. This groundbreaking theory has been confirmed by numerous experiments and observations, including the bending of light around massive objects and the precise orbit of planets. General relativity also predicts the existence of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. These waves, which travel at the speed of light, were first predicted by Einstein but were not directly detected until 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded waves generated by the collision of two black holes. The detection of gravitational waves marked a new era in astrophysics, allowing scientists to observe the universe in a completely new way. Instead of relying solely on light, we can now study the distortions in space-time itself, giving us insights into the most violent and energetic events in the cosmos. While gravity governs the behavior of large-scale objects like planets and galaxies, the strong nuclear force and the weak nuclear force operate on a much smaller scale, controlling the interactions of subatomic particles. These forces, along with electromagnetic force, form the foundation of the standard model of particle physics, which describes the fundamental particles and forces that make up the universe. The strong nuclear force is the most powerful of the fundamental forces. It binds protons and neutrons together in the nucleus of an atom, overcoming the electromagnetic repulsion between positively charged protons. Without this force, atomic nuclei would fall apart. The weak nuclear force, on the other hand, is responsible for certain types of radioactive decay, such as the decay of a neutron into a proton, an electron, and an antineutrino. These forces, while incredibly powerful, only act over very short distances on the scale of the size of an atomic nucleus. The electromagnetic force, which is responsible for the interactions between charged particles, governs everything from the structure of atoms to the behavior of light. It is the force that holds electrons in orbit around the nucleus of an atom, and is responsible for the entire electromagnetic spectrum, from radio waves to gamma rays. The electromagnetic force is one of the most well-understood forces in physics, and it plays a crucial role in the chemistry of life and the formation of matter. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are the building blocks of everything we know in the universe. Yet, despite our understanding of these forces, we still don't know how they are connected. For decades, scientists have sought a unified theory, often called the theory of everything, that would explain how all four forces fit together. One of the leading candidates for this theory is string theory, which proposes that the fundamental particles of nature are not point-like objects, but rather tiny vibrating strings. According to string theory, the different vibrations of these strings give rise to the various particles and forces that make up the universe. However, string theory remains highly speculative, and scientists are still far from finding a concrete testable theory that unifies all the forces of nature. While general relativity and quantum mechanics, the theory that describes the behavior of particles on the smallest scales, work remarkably well within their respective domains, they are fundamentally incompatible. The search for a unified theory that can explain both the large-scale structure of the universe and the behavior of subatomic particles remains one of the most elusive goals in modern physics. As we search for answers to these fundamental questions, we are also exploring some of the most extreme and mysterious phenomena in the universe, such as black holes, neutron stars, and gamma-ray bursts. These objects are the result of the most extreme conditions in the cosmos, where gravity and other forces are so powerful that they push the boundaries of our understanding of physics. Black holes, as we have discussed, are some of the most enigmatic objects in the universe. The point at the center of a black hole, known as the singularity, is a place where the laws of physics as we know them break down. The density of matter in a singularity is so great that it is effectively infinite, and the curvature of space-time is so extreme that not even light can escape. This makes black holes incredibly difficult to study. However, through indirect observations, such as the effects of black holes on nearby matter, the emission of X-rays from material falling into a black hole, and the detection of gravitational waves, we are beginning to piece together the mystery of these cosmic giants. Another fascinating object is the neutron star, which is formed when a massive star undergoes a supernova explosion and leaves behind an extremely dense core. Neutron stars are so dense that a single cubic centimeter of their material can weigh as much as a mountain. These stars are made almost entirely of neutrons, which are subatomic particles with no electric charge. Neutron stars are also known for their magnetic fields, which are billions of times stronger than Earth's. Some neutron stars, known as pulsars, emit regular pulses of radiation as they rotate rapidly, providing scientists with a natural cosmic clock that can be used to measure the passage of time with incredible precision. Perhaps one of the most dramatic events in the universe is a gamma-ray burst, GRB, which is the release of an enormous amount of energy in the form of gamma rays. These bursts are thought to occur when a massive star collapses into a black hole, or when two neutron stars merge. GRBs are the most energetic explosions known to man, releasing more energy in a few seconds than the sun will emit in its entire lifetime. They are so powerful that they can be observed from billions of light years away. The study of GRBs has provided valuable insights into the violent processes that shape the universe, including the formation of black holes and the merging of neutron stars. As we continue to explore these extreme phenomena, we also gain new insights into the broader structure of the universe. One of the most important discoveries of the past few decades has been the realization that the universe is not only expanding, but that its expansion is accelerating. This discovery, made in the late 1990s through the study of distant supernova, has led to the hypothesis that an unknown force, known as dark energy, is driving this accelerated expansion. Dark energy is thought to make up about 68% of the total energy content of the universe, yet we still know very little about it. The discovery of dark energy has profound implications for the future of the universe. If dark energy continues to drive the accelerated expansion, the universe may eventually expand so rapidly that galaxies, stars, and even atoms will be stretched apart, leading to what is known as the Big Rip. This is just one of several possible scenarios for the future of the universe, each of which depends on the nature of dark energy and other unknown factors. As we search for answers to the questions of the universe, we are reminded of how much we still don't know. The universe is an infinitely complex and ever-evolving system full of mysteries and unknowns. From the smallest subatomic particles to the largest galaxies, everything is connected by the fundamental forces that govern its behavior. And while we have made incredible strides in our understanding of the cosmos, the quest for knowledge is far from over. Each discovery brings with it new questions and new frontiers to explore. The universe is vast, and our journey to understand it is just beginning. The universe, as we've learned, is not just a random collection of stars, planets, and galaxies. It is a complex, interconnected system of forces and phenomena that work together to create the cosmos we observe. When we step back and consider the grand scale of the universe, we are reminded of the vastness and elegance of its structure. Galaxies, for example, are not just clusters of stars. They are the building blocks of the universe itself, shaping the very nature of space and time. A galaxy is a massive, gravitationally bound system that consists of stars, gas, dust, and dark matter. The Milky Way, our home galaxy, is just one of an estimated 100 billion galaxies in the observable universe, each containing billions to trillions of stars. The sheer number of galaxies is mind-boggling. To put it into perspective, if each galaxy contained just 100 billion stars, a modest estimate, that would mean there are 10 sextillion stars in the observable universe, an almost incomprehensible number. Galaxies come in various shapes and sizes, ranging from spiral galaxies like the Milky Way to elliptical galaxies and irregular galaxies. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure of stars surrounded by spiral arms. Our galaxy spans about 100,000 light-years across and contains an estimated 200 to 400 billion stars. The Milky Way is also part of a small group of galaxies called the Local Group, which includes about 50 galaxies, including the Andromeda Galaxy, our nearest large neighbor. Andromeda is on a collision course with the Milky Way, and in about 4.5 billion years, the two galaxies will merge, forming a new, larger elliptical galaxy. The study of galaxy formation and evolution has revealed much about the history of the universe. Galaxies are thought to have formed relatively soon after the Big Bang, within a few 100 million years. Initially, they were small and irregular, but over time they grew through processes like galaxy mergers and the accretion of gas and dust from the surrounding space. The early universe, before about 1 billion years after the Big Bang, was a chaotic and violent place, with galaxies colliding and merging at an unprecedented rate. These collisions triggered star formation and in the process created some of the most massive and energetic objects in the universe, including supermassive black holes. Supermassive black holes are now thought to reside at the centers of most galaxies, including our own. The one in the center of the Milky Way, known as Sagittarius *****, has a mass of about ****, 4 million times that of the Sun. While we cannot observe black holes directly, we can observe their effects on the matter around them. In some cases, matter falling into a black hole forms an accretion disk, a rotating disk of gas that heats up to extreme temperatures and emits intense X-rays. These black holes play a crucial role in the evolution of galaxies, influencing star formation and the distribution of matter in the galactic core. Beyond individual galaxies, the universe is filled with large-scale structures that further shape the cosmic landscape. One of the most intriguing discoveries of the past few decades has been the identification of the cosmic web, a vast, interconnected network of galaxies and galaxy clusters. This structure resembles a spider's web, with galaxies concentrated along filaments of dark matter, forming vast superclusters separated by enormous voids. The discovery of the cosmic web has fundamentally changed our understanding of how the universe is organized. Instead of galaxies being distributed randomly, they are arranged in a complex, large-scale structure governed by the interplay of gravity, dark matter, and dark energy. The cosmic web is not just an abstract concept, it is something that can be observed directly. Using large surveys like the Sloan Digital Sky Survey, SDSS, astronomers have mapped the distribution of galaxies across the universe and have found that they are not scattered randomly, but are organized into filaments, sheets, and clusters. These structures are the result of the gravitational pull of dark matter, which clumps together to form the backbone of the cosmic web. The gravitational attraction of dark matter draws galaxies toward each other, causing them to form large clusters and superclusters. One of the most significant discoveries in recent years has been the realization that the expansion of the universe is accelerating rather than slowing down as previously thought. This discovery, made in the late 1990s, revolutionized our understanding of the universe. When astronomers observed distant supernovae, they found that these stars were receding from us at an increasing rate. This led to the hypothesis that an unknown force, later dubbed dark energy, is driving the accelerated expansion of the universe. Dark energy is thought to make up about 68% of the universe's total energy content. Despite its overwhelming influence, dark energy remains one of the greatest mysteries in modern physics. It is not something we can directly observe, but we can see its effects on the universe's expansion. Dark energy is believed to have a repulsive effect, causing galaxies to move apart at an ever-increasing rate. Some scientists believe that dark energy is a property of space itself, while others think it could be a manifestation of a fundamental force that we have yet to understand. The discovery of dark energy raises important questions about the ultimate fate of the universe. If the expansion continues to accelerate, the universe will eventually reach a state where galaxies are so far apart that they can no longer interact with each other. This scenario, known as the Big Freeze, suggests that the universe will continue to expand forever, with stars burning out and galaxies drifting into the void. Another possibility, the Big Rip, suggests that the expansion of the universe could accelerate to the point where even atoms are torn apart. As we consider the future of the universe, we also look at the future of exploration. Humanity's curiosity has always driven us to explore the unknown, and space is no exception. The exploration of space has already brought us unimaginable discoveries, from the first human landing on the moon to the detection of exoplanets in distant star systems. But the road ahead is filled with even more exciting possibilities. One of the most ambitious goals for the future of space exploration is the colonization of Mars. For decades, scientists have speculated about the possibility of humans living on the Red Planet. Recent missions by NASA, such as Perseverance and Curiosity, have brought us closer to this goal by studying the planet's geology and searching for signs of past life. In addition, private companies like SpaceX, led by Elon Musk, are actively working on developing technology to send humans to Mars and establish a permanent colony. The challenge is immense, as the harsh conditions on Mars, such as its thin atmosphere, extreme temperatures, and lack of liquid water, make it a difficult place to live. Yet, despite these challenges, the prospect of colonizing Mars has captured the imagination of people around the world. In addition to Mars, the outer reaches of the solar system remain a prime target for exploration. NASA's Voyager missions, which launched in the 1970s, have already traveled beyond the orbit of Pluto, entering interstellar space, and sending back invaluable data about the outer solar system and the environment of space beyond. The New Horizons mission, which flew by Pluto in 2015, provided the first detailed images of the dwarf planet and its moons, revealing a complex and dynamic world. Beyond the outer planets, comet missions like Rosetta have provided us with a deeper understanding of the primordial building blocks of the solar system, offering clues about the early stages of planetary formation. Even more ambitious are the plans to explore other star systems. One of the most exciting projects currently in the works is the Breakthrough Starshot initiative, which aims to send tiny, lightweight spacecraft to the nearest star system, Alpha Centauri, within a generation. By using powerful lasers to propel small, light sail-equipped probes, Breakthrough Starshot aims to reach Alpha Centauri in just over 20 years, sending back data about the star system and its potential for supporting life. While the technology required to make such a mission a reality is still in its infancy, the potential for interstellar exploration is within our grasp. As we look to the stars, it is important to remember that our understanding of the universe is still in its infancy. The discoveries of today are only the beginning of what we will learn about the cosmos in the coming centuries. The future of space exploration is filled with infinite possibilities, from the colonization of other planets to the discovery of new forces and phenomena that challenge our understanding of space and time. The universe is vast, and humanity's curiosity is boundless. The journey ahead will be one of exploration, discovery, and wonder, As we push the boundaries of knowledge and venture further into the unknown, the mysteries of the universe continue to unfold before us, and each new discovery brings us closer to understanding the nature of our existence and our place in the cosmos. From the smallest particles to the largest galaxies, the universe is a never-ending source of inspiration and inquiry. And as we continue to explore it, we will no doubt find new questions to ask, new frontiers to explore, and new wonders to behold. As we stand on the edge of the known universe, it is impossible not to be struck by the enormity of what lies before us. From the creation of the cosmos in the Big Bang to the discovery of black holes and the revelation of dark energy, humanity has come a long way in understanding the fundamental forces that shaped the universe. Yet, despite the progress we've made, we are still only scratching the surface. The universe is far more vast, complex, and mysterious than we can even begin to comprehend, and as we look forward, we see an endless expanse of exploration, discovery, and questions that remain unanswered. One of the most profound realizations we have come to in recent years is that the universe is not a static entity. It is a dynamic, constantly evolving system with galaxies, stars, and planets, all undergoing changes that we are just beginning to understand. The expansion of the universe, for example, continues to accelerate, driven by a force we don't yet fully understand: dark energy. This discovery has completely transformed our conception of the cosmos, challenging the very nature of space-time itself. As the universe expands at an ever-increasing rate, we are left with one of the most fundamental questions of all: what is the future of the universe? Many scenarios have been proposed, each with its own implications for the ultimate fate of the cosmos. One possibility is the Big Freeze, where the expansion of the universe continues indefinitely, causing galaxies to drift further apart until the universe becomes cold and dark. In this scenario, stars burn out, and the universe slowly becomes inhospitable to life. This is the most widely accepted theory, as the evidence for the accelerated expansion of the universe seems to point in this direction. However, other possibilities exist. The Big Crunch theory suggests that the universe's expansion could eventually slow and reverse, causing everything to collapse back into a singularity. This would be the opposite of the Big Bang, a catastrophic collapse that might lead to another cycle of cosmic rebirth. More recently, some scientists have proposed the idea of a Big Rip, where the force of dark energy becomes so powerful that it overcomes even the fundamental forces of nature, tearing apart galaxies, stars, planets, and even atoms. While the ultimate fate of the universe remains uncertain, one thing is clear: the universe is in a constant state of change. Its future will be shaped by the forces we are only beginning to understand. As we continue to explore the cosmos, the discovery of new forces and phenomena may alter our understanding of how the universe will evolve in the future. The search for the true nature of dark energy, for instance, could hold the key to unlocking the ultimate fate of the universe. Until then, we are left to ponder the possibilities, knowing that the universe's future is as mysterious and unpredictable as its past. In parallel with our exploration of the universe's future, we must consider the future of humanity in space. As our technology advances, we are no longer limited to observing the stars from afar. We are beginning to venture into the cosmos ourselves. The possibilities for humanity's future in space are vast and varied, from the exploration and potential colonization of Mars to the possibility of reaching other star systems. Our progress in space exploration is a testament to humanity's resilience, curiosity, and ingenuity. One of the most exciting prospects for the future of space exploration is the colonization of other planets, particularly Mars. For decades, scientists and visionaries have speculated about the possibility of humans living on the Red Planet. The idea of building self-sustaining colonies on Mars has captured the imagination of people all over the world. Recently, organizations like NASA and private companies such as SpaceX have taken significant steps toward making this dream a reality. The Perseverance rover, launched in 2020, is currently studying Mars's geology and climate, searching for signs of past life and paving the way for future human missions. SpaceX, under the leadership of Elon Musk, is actively developing the Starship, a spacecraft designed to carry humans to Mars and beyond. The goal is to establish a self-sustaining colony on Mars within the next few decades. While the challenges are immense, ranging from the lack of a breathable atmosphere to the harsh surface conditions of the planet, the potential for humanity to become a multiplanetary species is an exciting and realistic prospect. In addition to Mars, the outer planets and their moons present exciting opportunities for exploration. Europa, one of Jupiter's moons, is a prime candidate for the search for life beyond Earth. Scientists believe that beneath Europa's icy surface lies an ocean that could harbor microbial life. In recent years, missions like NASA's Europa Clipper have been planned to explore this moon in more detail, probing its ice-covered ocean and searching for signs of life. Similarly, Saturn's moon Titan has been identified as a key target for future exploration, as its atmosphere and surface conditions offer intriguing possibilities for the development of life, albeit in a form vastly different from anything we are familiar with on Earth. In the longer term, the possibility of exploring other star systems remains one of the greatest ambitions in space exploration. One of the most exciting projects currently in the works is Breakthrough Starshot, a mission aimed at sending small, lightweight probes to the nearest star system, Alpha Centauri, within a generation. These probes, propelled by powerful lasers, could travel at 20% of the speed of light, reaching Alpha Centauri in just over 20 years. While this mission is still in its early stages, it represents the first real step toward interstellar exploration. The idea of sending probes to explore planets around nearby stars is no longer the stuff of science fiction. It is becoming a reality. The future of space exploration will not only expand our understanding of the universe, but also push the boundaries of technology, engineering, and human capability. It will require international cooperation, immense investment, and the willingness to take risks in the pursuit of knowledge. The human spirit of exploration, driven by our desire to answer the fundamental questions of existence, will propel us further into the cosmos than we ever thought possible. As we look to the future of space exploration, we are also faced with the ethical challenges that come with venturing into the unknown. As humanity pushes into space, we must confront important questions about our responsibilities to the environments we encounter, whether it's on Mars, Europa, or other celestial bodies. How do we ensure that we don't repeat the mistakes we've made on Earth, destroying ecosystems, overexploiting resources, or contaminating pristine environments? These questions are not just scientific, they are ethical and philosophical, challenging us to think deeply about our place in the cosmos and the impact we will have on the worlds we explore. The mysteries of the universe remain vast, and with each discovery we find that there is always more to learn. The search for extraterrestrial life, the exploration of distant galaxies, the understanding of dark energy and dark matter, these are the frontiers of science that will continue to shape our future. But perhaps the greatest discovery of all is the realization that the universe is not just something to be studied from a distance. It is something we can explore, understand, and eventually call home. As humanity takes its first steps beyond Earth, we must remember that we are part of something much greater than ourselves. The universe is not a place of isolation. It is a place of connection, of interdependence, where everything from the smallest particles to the largest galaxies is part of an intricate and beautiful web. Our exploration of the cosmos is not just about discovering new worlds, it is about discovering ourselves. And as we venture further into the unknown, we will continue to ask the same timeless questions. What is the nature of existence? Where do we come from? What is our place in the universe? And perhaps most importantly, what will the future hold? The universe, in all its vastness and mystery, will always be there to answer, one discovery at a time.